So, I'm going to talk about the research we've been doing on collective decision making, and more specifically how we introduced confidence and value estimates to improve performance over previous methods. So first, let me explain what we mean by collective decision making. So first off, decision making. So we are repeatedly given problems, and for each problem we are given a set of decisions we can make. The goal is to consistently make good decisions. So how do we define what a good decision is? Well, we consider problems wherein the outcome is not subjective. So for example, consider the problem of medical diagnostics, wherein we need to deal with a patient who is ill, and we wish to determine the most appropriate treatment for that patient. Well, for example, the treatment with the highest probability of success. While this is something we could try to achieve through machine learning techniques, it makes sense to exploit the knowledge of medical experts to tackle this problem. This is where the collective part comes into play. So, whether it's medical experts or other types of experts to deal with different problems, we formalize the use of experts as a problem of deciding with expert advice. So concretely, experts are informed about the problem and they are then asked to provide advice in the form of a probability distribution over the arms. And in its simplest form, this is their preferred decision. So given that advice, we can aggregate it to make a decision, for example, through a majority vote. So this probability advice is a type of advice that has been considered before in the setting of deciding with expert advice, but one of the first things we looked at was whether restricting ourselves to probability advice was really necessary. So I say restricting because often probability advice is a relative measure of quality derived from a more informative absolute measure of quality. So this absolute measure of quality is an estimation of the expected outcome of each decision. Hence, rather than saying I prefer decision A over decision B, which is what probability advice tells us, value advice would tell us I expect decision A to have a 90% success rate and decision B to have a 50% success rate. Now, the crucial element here is that the uncertainty about one of the decisions affects the probability advice for all other decisions, whereas when using value advice, this uncertainty does not spread. So for the sake of completeness, we decided to also consider this value advice. Now again, we can simply aggregate value advice by averaging the advice over all the experts and making a decision based on this average. Now in both this case and the majority vote proposed for probability advice, we treat experts equally. When experts aren't uniform in their expertise, however, we can give a higher importance to the better experts. So instead of a simple average, we can use a weighted average, wherein the weights are determined by the performance of the experts. So, because we solve multiple problems with a set of experts, we have the opportunity to learn appropriate weights by iteratively increasing the weights of experts whose advice leads to good decisions. And this is what XP4P aims to achieve by balancing on one side exploitation, which is assigning high weights to experts we believe are good, but also on the other side, exploration, so which is the idea that you should give a chance to experts about which you are uncertain. There are, however, issues with this adaptive approach. First, obviously we start from scratch, which means that bad experts can have a high impact in the early stages, which can lead to bad performance. And second, XP4P does not condition the weights on the problem at hand, which means that problem-specific expertise cannot be identified. Now, it occurred to us that a straightforward approach to determining these weights that had not been considered in this setting was the use of confidence estimates. So, what do we mean exactly by confidence estimates? Well, concretely, in addition to their advice, we also ask experts to tell us how good they believe their advice is. We can then use this confidence, for example, in a weighted majority vote, in which case we blindly trust the confidence to be accurate, or instead we proposed XP4P plus con, which adapts XP4P to make use of this confidence by using it as a prior on the expert weights it maintains. So instead of initializing the weights uniformly, we initialize the weights based on the provided confidence. Right, so we have these different alternatives, and to evaluate the performance of these alternatives, we set up an experimental evaluation. Okay, so we used an artificial experiment, which allows us to control the number of experts, the number of alternative decisions, as well as how confidence is generated. So concretely, we train n artificial experts on an artificial bandit. So the bandit is the problem. We sample a set of possible decisions at each time step and ask experts for advice about those decisions. And then, based on that advice, we make a decision and observe a reward, which is the outcome of the decision we made. So for example, 1 if the decision we made led to a successful outcome, and 0 otherwise. Now, performance is measured in terms of regret, which is the distance between the cumulative success of the best expert and the cumulative success of the collective decision-making algorithm which we are considering. So which means that a regret of 0 means that we perform as well as the best experts, and regret below 0 means that we outperform the best experts. So let us first look at our baseline performance without confidence estimates. So we look at either having lots of experts and few arms, which is on top, or having a lot of arms but only a few experts on the bottom. Algorithms in blue use probability advice, algorithms in orange use value advice. So we have XP4P, which learns to weight experts, so that's our adaptive method, and the weighted majority vote, which simply averages their advice, in this case of no confidence. So the dotted line marks the performance of the best experts, and anything below it performs better than the best experts. So what we see here, and which is interesting here, is that the performance of the adaptive method is not necessarily better than a simple weighted majority vote. Now, the reason for this is that experts are expected to be better than random, and so when we combine the advice of several experts, we average out individual errors, which brings about a large increase in performance, which allows us to surpass actually XP4P. So what happens then when we introduce confidence estimates? Well, simply put, we observe a significant improvement in performance for all methods. One interesting observation is that XP4P plus con seems to benefit less from confidence estimates than the weighted majority vote. The primary reason for this is that while we initialize XP4P plus con with appropriate weights, it is still a stochastic method which might slightly diverge away from the weights that we used to initialize, so from the confidence based weights. So an obvious question then is, why should we even consider XP4P plus con if the weighted majority vote is better? Well, to answer that, we have to take into account that accurate confidence estimates, such as those used in these results, are highly unlikely in a real scenario. Right? If we consider, for example, human experts, well, research has shown that humans tend to be biased in their self-evaluation, which in this setting translates to over or underestimating confidence. So as a follow-up on the previous results, we asked how noise in the confidence estimates affects our methods. So our noise model samples for each expert n a noisy confidence from a beta distribution parameterized by the true confidence of that expert, which is C and T, and a noise level eta. To illustrate this noise model, we have here on the right the resulting confidence distributions for an expert with a true confidence of 0.8. Now, as you can see, as the noise level increases, the distribution from which we sample the noise confidence tends towards a uniform distribution. So when the noise is high, the confidence is unrelated to the actual performance of the expert. Right, so let's look at how this affects performance. Okay, we plot again here the regret for our two algorithms. This time the x-axis is the noise level, so the further right we go, the less accurate the confidence estimates are. We have in orange the weighted majority vote, and in blue XP4P plus con. Dashed lines use value advice, solid lines use probability advice. Right, then we have again the distinction between a lot of arms, few experts, and few arms, a lot of experts. Right, so the crucial observation here is that as noise levels increase, the performance of the weighted majority vote degrades more rapidly than the performance of XP4P plus con. So while XP4P plus con benefits slightly less from a perfect confidence estimate, which are unlikely to begin with, it is far less affected by noisy confidence. So this suggests that it should be preferred if we are uncertain about the accuracy of the confidence estimates. So, in conclusion, we looked at the state of the art in collective decision making, formulated as the problem of deciding with expert advice, and we proposed enhancements based primarily on the use of confidence estimates. We confirmed that while accurate confidence estimates can significantly improve performance, one should be careful as inaccuracies in reported confidence is likely, and so we should not blindly trust them. But instead, we should prefer an adaptive method such as our proposed XP4P plus con. Finally, as a follow-up, we have another talk called Collective Decision Making as a contextual multi-arm bandit, which proposes a different approach to solving this problem, which I highly invite you to watch as well. Thank you.